Okay, and we're back. So what we're looking at here is a current carrying wire. If you look at it right there, so the wire is red, it's carrying current to the left, and we're going to figure out what the equation or what the magnitude is for the magnetic field at this point, which is some distance capital R above the wire. It is some distance little r from our little current length IDS, and that is some horizontal distance S away from being directly beneath point R. So if we go with the generic equation, then we just have dB equals mu naught I cross ds over 4 pi r squared. That's the Biot-Savart law. And then you integrate both sides. The left side, just dB, just jumps right to B. And then the cross product, this I cross ds part, this second line is really the exact same thing, but rewritten instead of I cross ds, it's written as what the cross product is, which is I ds sine theta. So same thing, just get rid of the cross symbol and write it as I ds sine theta. So the next part, then, we're going to have to start playing the game where we're going to have to be able to talk about the changes that are going to occur in this equation as we move our little current length around. So what's going to happen here is we're going to take IDS and we're going to be sliding it along this length of wire all the way down and back. And what that means is certain things are also going to be changing. So if we change location of our current length, then it shouldn't be hard to imagine that little r would change. It also shouldn't be hard to imagine that S, oops, sorry, it's not quite the change I wanted to have happen, that S would change. There we go. That S would change as well. And then also, as we move that, then theta would change. And so we've got three variables changing. And we want to be certain that when we do an integral that we only talk about the change occurring through one of them. And the variable through which we're going to change is going to be theta, which means we're going to have to find ways to say little r and little s in terms of theta. So that brings us to our third line. And what we've done is we've pulled out everything that's a constant to the left of the integral. And that leaves us with what you can see on the right, the ds sine theta little r squared. And so the first thing we're going to go after is that little r term. So if you go back and look at that picture, sine of theta here would involve big R, which never changes, theta, which would change, uh, and the hypotenuse, which is little r. So what we're going to have to do is we're going to have to say little r in terms of either something that doesn't change, which is big R, and theta, which is the variable that we want to have the change in. So that means we can just rewrite little r as big R over sine theta, and that's how it's rewritten right here. And then the next thing we're going to go after is, so that's how it's rewritten here. And then the sine squared theta flips up to the top, and that's why we have the sine cubed theta here. That's where that comes from. Next thing we're going to go after is going to be that ds term. And so that'll be written as, if you go back to the image, and you can scroll up at any point or look at it in the notes, tan theta is big R over S. So rearranging, S equals R over tan theta. And then we get S equals R cotan theta. And then we still need to take a derivative out of this. So you have to take derivative with what's going to change, which is d theta. So ds d theta. Take the derivative cotangent, which is negative cosecant squared. Rearrange for ds, and we're at negative r cosecant squared theta d theta. And that might be a good spot to press pause for right now.